Okay. So in the last lecture, we have started with some vehicle fundamentals, right? And in the previous lecture, we have seen the general description of vehicle movement, right? We have defined that equation of acceleration, which was given by dv by dt is equal to sigma ft minus sigma ftr divided by delta mv, right? Where v was our vehicle speed, sigma ft is total tractive effort, and sigma ftr is the total resistances, right? And mv here we have considered as total mass of the vehicle, and delta represents the mass factor. Okay, so which is nothing but in effect of rotating components in the powertrain. So whenever we apply the total tractive force, we are subtracting this much amount of force, which is because of the resistance. And we have seen we are available with total three types of resistance: rolling resistance, aerodynamic drag, and grading resistance. All these resistance we have seen, and we have derived the equation for these particular resistances. Okay, so when we talk about the road resistance, total road resistance, then total road resistance is given by this equation: FRD is equal to FF plus FG, and which was equal to MV into G FR cos alpha plus sin alpha, right? And we have also seen that if the condition road angle is very much small, then the same equation can be written as MVG into FR plus I, right? So that was our equation, and here I is the grade. Okay, I is the grade, which was nothing but the ratio of H by L, and which was approximately equal to tan alpha, and we have considered it as an sin alpha only, right? Because the road angle usually is replaced by the grade value when the angle is very much small, right? So this is what we have seen. Now you are aware about the rolling resistance, aerodynamic drag, and grading resistance. Okay, so any vehicle is given to you, you will be able to find out all the three resistances and the total tractive effort by this resistance, by this resistance, right? So we have seen this particular case, right? This is nothing but the different forces acting on a vehicle. Specifically, we are talking about the electrical vehicle. Okay, so in this longitudinal direction, the major external forces acting on this two axle vehicle includes the rolling resistance of the front end and rear tires. You can see, right, here with the green line. This is as FRF and FRR. Okay, and these are represented by the rolling resistance moment TRF and TRR. Then we have aerodynamic drag over here. So this aerodynamic drag is given by FW, and the grading resistance, which is equal to MVG into sin alpha. Okay, so these are the three resistance, and we have tractive effort to the front and rear tires. This is FTF over here, FTF and FTR. Okay, now based on these two, if I talk about this FTF and FTR, FTF and FTR. Okay, so this value depends on which driving mechanism we are going to use. Okay, FTF will be equal to 0 for a rear wheel driven vehicle. Okay, when our vehicle is rear wheel driven, and FTR will be equal to 0 for a front wheel driven vehicle, right? So this was the things we have covered up till now. Now We know the vehicle movement very well. We know the resistances offered by this vehicle very well, right? So will try to define now, derive now the dynamic equation, okay? Because this dynamic equation will help us in modeling the drive or modeling the vehicle, right? So the dynamic equation of a vehicle motion along the longitudinal direction will now be expressed by, okay, we already know it is given by this dv by dt is equal to sigma ft minus ftr divided by delta mv, right? So the dynamic equation is given by mv dv by dt will be equal to ftf plus ftr minus frf plus frr plus fw, this is aerodynamic drag, and fg because force because of the grading resistance. Okay, let us call this equation as equation number 1. So here if you can see this dv by dt, this is nothing but the linear acceleration of the vehicle. Okay, this term dv by dt represents linear acceleration of the vehicle, right, along the longitudinal direction. And mv we know it is vehicle mass. mv is nothing but vehicle mass. Okay, so you can see the right hand side equation here. Okay, on the right hand side of the equation, the first term is the total tractive effort, right? And the second term is the resistance. Okay, if we talk about this, the first term of the equation, this represents the total tractive effort, and if I talk about the second term, this is nothing but the total resistance. Okay, so this is my complete dynamic equation of an vehicle, electric vehicle. Now to predict the maximum tractive effort that the tire ground contact can support on the normal loads on the front and real axles have to be determined. Okay, so by adding the moments, by summing the moments of all the forces about some center point, right, which is nothing but the center of the tire ground area. Okay, then the normal load on the front axle will be determined. Okay, so let us say the normal load on the front axle is wf. Okay, I am talking about this particular case. See, what we are interested in finding out this parameter wf, which is nothing but the normal load on the front wheel or front axle, right? So what we need to do, by adding the moments of all the forces about the point r. Okay, so let us say my point r is the center of the vehicle over here, right? So what will happen now, wf will be equal to mvg times lb cos alpha minus trf plus trr plus fw hw plus mvg h sin alpha plus m hg dv by dt. Okay, and this entire equation needs to be divided by length of the vehicle, that is L. Okay, so this is, let us call this as an equation number 2, right? So this was the load acting on the front axle. Similarly, we have to find out the load, normal load acting on the rear axle, right? So similarly, the normal load acting on the rear axle can be represented as WR, and it is given by mvg LA cos alpha minus TRF plus TRR plus RWSW plus mvg HG sin alpha plus mvhg dv by dt. Divided by L. Let us call it equation number 3. Okay, so these are my normal load which are acting on the front axle as well as rear axle. Okay, these are also the dynamic equations. Now consider we are running the passenger car. Okay, so for passenger cars, the height of the center of application of aerodynamic resistance, if I talk about HW, let us say over here. Whenever we talk about this, okay, I have to see HW over here, right? And this is the HG. This is my two lengths LA, LB, and this is our total length L between the centers of the two axle, front axle and rear axle, right? So for passenger cars, what will happen? The height of the center of the application of aerodynamic resistance HW is assumed to be near the height of the center of the gravity of the vehicle, that is HG, as I have told you over here. Okay, these are two same. HW will be considered is equal to HG. Then in that case, what will happen? We can further reduce or we can simplify this equation number 2 and equation number 3. Okay, so what will happen to equation number 2 now? So I'm talking about the WF. It will become LB by L MVG cos alpha minus HG by L FW plus FG plus MVG FR RD by HG cos alpha plus MV dV by dt. Okay, this will be the reduced equation, right? Do not worry how these equations are determined or derived. Okay, this is the part of automobile engineering, right? So we will directly use this equation. These are very well established equations which we are going to use for our purpose. Okay, specifically talking about modeling of electric vehicles. Okay, so we'll be directly taking all these equations which are already established. We need not to derive this equation one more time. We will accept in the form as they are. Okay, and if we talk about the normal load acting on the rear axle, then WR will be equal to LA by L MVG cos alpha plus hg by L Fw plus Fg plus mvg Fr into Rd by Hg cos alpha plus mv dv by dt. Okay, so here you can see the term new term Rd. Rd is nothing but the effective radius of the wheel, right? So these are the equations. Now in the last lecture, if you remember, we have derived the equations. Okay, one equation was there. Let me write down this equation one more time, which was related to the road angle. Okay, we know that Fr is given by Pfr cos alpha. Okay, this was the equation where we have considered this P as normal load, which is acting on the center of the rolling vehicle. Okay, so when a vehicle is operated on a slope road, right, the normal load capital P should be replaced by some component, okay, which is perpendicular to the road surface, and that is why this equation was there. Fr is equal to Pfr cos alpha, where alpha is the road angle. Okay, in case of this figure here, alpha is there. Okay, this is our road angle. Our vehicle is moving up a grade, right? So this was our equation of interest, right? Now if I use this equation and the equation which I have written over here, this one, equation number 1. Okay, so from these two equations, again we can reduce these equations of Wf and Wr. Okay, so let us write down. Wf is given by Lb by L mvg cos alpha minus hg by L ft minus fr 1 minus rd upon hg. Okay, and load acting on a rear axle will be equal to La by L mvg cos alpha plus hg by L ft minus fr into 1 minus rd by hg. Okay, so these are our two new equations. Let us call it equation number 6 and equation number 7. Okay, so here I have considered the ft. Okay, so ft, this total tractive force ft, is nothing but ftf plus ftr. Okay, this is the total tractive effort of the vehicle. And if I talk about this fr I have considered is total rolling resistance of the vehicle. Okay, so now if you can see equation number 6, then the first term on the right hand side of this equation number 6 and equation number 7 is the static load on the front and rear axle when our vehicle is at rest on level ground. Okay, so these two, if I talk about the first term of equation 6 and the first term of equation 7, these are the static load on the front and rear axle. Static load on the front and rear axle when my vehicle is at rest. When vehicle is at rest on level ground. Okay. And if I talk about the second term is nothing but the dynamic component of the normal load. Okay. So these two terms, second term of equation 6 and second term of equation 7, will be nothing but dynamic component of normal load. Okay, so we do have static component as well as dynamic component of the normal load, right? Now, the maximum tractive effort that the tire ground contact can support. Okay, this is nothing but the any small amount over this maximum tractive effort will cause the tire to spin on the ground. Okay, so this maximum tractive effort is usually described by the product of the normal load and coefficient of road adhesion. It is denoted by mu. Okay, or it is also referred to as the frictional coefficient in some books or in some literatures whenever you will go through the literatures of electric vehicle. Okay, so now we know if we want to find out the maximum tractive effort, right, then this maximum tractive effort is nothing but the product of the normal load and the coefficient of the road adhesion. Okay, so ft max in our case, ft max is given by mu wf. Okay, so this is our equation. Now we know f very well. Okay, it is already, we have derived already lb by l mvg cos alpha minus hg by l ft max minus fr into 1 minus rd upon hg. Okay, so this is our new equation. Okay, okay, just simplify this equation and we will get the new equation ft max, which is equal to mu mvg cos alpha into lb plus fr hg minus rd divided by l upon 1 plus mu hg divided by l. Okay, let us call this equation as equation number 8 and this is my equation number 9. Okay, so here fr term is there. Fr is nothing but the coefficient of rolling resistance. Okay, here over here, this term, this is nothing but coefficient of rolling resistance, right? Similarly, this is the maximum tractive effort for front end axle. Okay, similarly we can find out the maximum tractive effort for a rear wheel driven vehicle. Okay, so for a rear wheel vehicle driven vehicle, for a rear wheel driven vehicle, this ft max will be mu into wr. Again, wr is very well known to us. Okay, we already have derived the equation. It is given by la by l mvg cos alpha minus hg by L ft max minus fr into 1 minus rd upon hg. Okay, just simplify this equation and we will get the final equation of ft max for a rear wheel driven vehicle, and it is equal to mu mvg cos alpha into La plus fr hg minus rd divided by L over 1 plus mu hg divided by L. Okay. Let us call this equation as equation number 10, and this is my equation number 11. Okay, so these are the maximum tractive effort when the vehicle is front wheel driven or a rear wheel driven. Okay, so we will be using this equation, either equation number 9 or equation number 11, as for finding out the maximum tractive effort required for the vehicle, right? So in vehicle operation, the maximum tractive effort on the driven wheels transferred from the power plant through some transmission, and it should not exceed the maximum value that are limited by the tire ground cohesion. Okay, and what is the tire ground cohesion? Right, mu, value of mu. Otherwise, what will happen? The driven wheels will spin on the ground and it will lead to the instability of the vehicle. Okay, so this is having much important. What is the tire ground adhesion? Right, because it will limit our maximum tractive effort that can be generated. Right, it should be limited. It should not exceed the maximum tractive effort value, which is given by ft max. Okay, so now let us try to understand this tire ground adhesion, and we'll try to relate some with the maximum tractive effort, right? So when the tractive effort of a vehicle exceeds the limitation of the maximum tractive effort due to the adhesive capability between the tire and the ground, what will happen? The drive wheels will spin on the ground. That is what we have seen. Actually, what happens? The adhesive capability between the tire and the ground is sometimes the main limitation of the vehicle performance. And this is especially true when the vehicle drives on wet, icy, snow covered or soft soil roads. Okay, in this case, what happens? A tractive torque on the drive wheel would cause the wheel to have significant slipping on the ground, and the maximum tractive effort on the driven wheel depends on the longitudinal force that the adhesive capability between the tire and ground can supply, rather than the maximum torque that the engine can supply. Okay, and lots of experimentation have been done, and these experimental results show that on various types of ground, the maximum tractive effort of the drive wheel closely relates to the slipping of the running wheel. Okay, and this is also true on a good paved dry road where the slipping is very small due to the elasticity of the tire. Okay, so we need to define a new term which is called as slip. Okay, and this slip of a tire usually defined as the slip of a tire usually defined as S equal to 1 minus V by RW, and it is measured in terms of percentage. Okay, or 1 minus RE by R into 100. Okay, so this is the V. Okay, so here if I talk about this particular capital V, then capital V is nothing but the translatory speed of the tire center. W, or you can say omega, is the angular speed of the tire. Small r is the rolling radius of the free rolling tire, and Re is the effective rolling radius of the tire, okay, which is also defined as the ratio of translatory speed of the tire center to the angular speed of the tire. Okay, so in traction, when we talk about the speed V is less than the R omega, and therefore slip of the tire has a positive value between 0 and 1, right? Whenever we are accelerating the vehicle, at that time the value of slip will be positive and it will be in between 0 to 1. But during braking, we have to redefine the slip. Okay, so during braking, what happens? During braking, the tire slip would be defined as 1 minus R omega by V. Okay, or 1 minus R by Re. You can see the term has been interchanged compared to the previous equation. Okay, let us call this equation as equation number 13. Okay, and this slip will also have a positive value between 0 and 1, similar to the traction. Okay, so the maximum traction effort of a tire corresponding to a certain tire slip is usually expressed as Fx is equal to P mu. Okay, so here P is nothing but the vertical load. Okay, P is nothing but the vertical load of the tire, and mu, as we know, it is the tractive effort coefficient. Tractive effort coefficient. Okay, which is a function of the tire slip. Okay, so the tractive effort coefficient and tire slip will have a relationship. If we try to draw, then it will have some kind of relationship. Let us draw the relationship. Okay, on x-axis I am taking the slip which is ranging from say 0 to 100%. Okay, so somewhere here we will get our 50%, and on the y-axis I am taking mu, which is nothing but tractive effort coefficient, right? So suppose we consider the longitudinal slip. Okay, so in that case, what is going to happen? We will have this kind of slip. It will increase and then it will reduce somewhat. Okay, so this particular level, you can see this is our level mu s, right? Okay, and this is the maximum level over here. Let us call this level as mu p. Okay, so this is for the longitudinal movement. Okay, so this was the case, right? And whenever we have the lateral slip of tires, at that time the curve will be like this. Okay, it will be maximum, then it will increase, and when slip becomes 100%, the tractive effort, or sorry, not tractive effort, but tractive effort coefficient will become 0. Okay, this is our lateral case, right? So this is what we have seen, the relationship between the tractive effort coefficient and tire, right? Now let me define these terms. Say this is my 0, this is point A, here is point B, okay? And at this maximum value, let us say my slip is 15 to 20%. Okay. So if I talk about this section OA, okay, this is, what is this? It is the small slip range, right? And in this small slip range, you can see the tractive effort is almost proportional to the slip value. Okay, it is increasing linearly, you can see. Okay, though it is very small, I am talking about this portion. Okay, where my slip range is very much small, say 0 to 15 or 20. So in that case, if you can see the tractive effort, it has a linear relationship between the slip value. Okay. So this small slip is caused by the elasticity of the tire rather than the relative slipping between the tire and the ground at the contact patch. Okay. When a tractive torque is applied to the tire, what will happen? A tractive force is developed at the tire ground contact patch. And at the same time, the tire tread in front and with the contact patch is subjected to compression. Right? So a corresponding shear deformation of the sidewall of the tire is also developed. And as you know, the tread elements are compressed before entering the contact region. The distance that the tire travels will be less than the distance in a free rolling tire. Okay. So because of the nearly linear elastic property of the tire, the tractive effort slip curve is almost linear, as we can see. Okay. Then if we further increase the wheel torque, okay, so a further increase in wheel torque and tractive force will result in a part of the tire tread sliding on the ground. And under these circumstances, the relationship between the tractive force and the slip is going to be nonlinear. Okay, and this corresponds to this section AB. You can see now there is a nonlinear relationship from curve A to curve B. Okay. So the peak tractive effort is reached at this particular point at a slip of some 15 to 20%, right? And a further increase in slip beyond this results in an unstable condition, right? You can see. So the tractive effort coefficient falls now rapidly from the peak value to the purely sliding value, right? You can see in this particular figure, right? So for normal driving, the slip of the tire must be limited in a range than 15 to 20%. Okay. So we have the peak values of this adhesion and sliding values of this adhesion for different types of roads. So we need to take care of this particular road, okay, and act correspondingly. Okay. So suppose I am talking about the concrete road. If my road is made up of concrete, then the peak value mu p and slipping value mu s, sliding value mu s, we are talking about these two value on a concrete road, then it will be equal to 0.8 to 0.9 and it will be equal to 0.75, the sliding value. If I'm talk about the road which is made up of asphalt, in that case the peak value will be 0.8 and sliding value will be 0.7. Okay. If we have the gravel, then the peak value is 0.6 and sliding value will be 0.55. Okay. If we have earth road, okay, earth road, let us say dry condition, right? In that case, the peak value is 0.68 and this is 0.65. Then earth road with wet condition. Earth road with wet condition. In that case, the value is 0.55 and slipping value will be from 0.4 to 0.5. Okay, if I talk about the snow, we are on snow, then in that case, peak value will be only 0.2 and sliding value will be 0.15. And if we are on ice, then it further reduces. The peak value will further reduce to 0.1 and sliding value will be 0.07. Okay. So these are this particular table shows the average value of tractive effort coefficient on various kind of roads. Okay. So we need to take care of this particular thing. Okay. You understand the behavior of a tire under the action of this driving torque. Okay. Now let us try to understand the powertrain tractive effort and the relationship between the speed of the particular vehicle. Okay. So we know an automotive powertrain. Okay. Suppose I am talking about some powertrain. Okay. Let me try to draw this powertrain first. And automobile powertrain. Okay, so we will have one engine, right? Okay, so say this is my engine first. Right. Then I have the transmission. Okay, so here this is called say clutch or torque converter. Okay, so we have this clutch over there, and then there is a box which is called as transmission. Okay, so in this particular box, transmission is going to happen. Okay, now this transmission will nothing but the weight of some gears and etc., right? So let us say this is our transmission. Like this, right? And then there will be one differential which is connected with the two wheels, okay, connected to the driven wheel via drive shaft. Okay, so we will have this differential over here. Okay, let me draw this line over there. And here is my differential. Okay, this will be our drive shaft, and to this drive shaft our vehicle has been connected. Okay, so this is my vehicle. Sorry, not vehicle but the wheel. Just complete the entire phenomena. Okay, so this will be our differential box. Okay, right. So we do have our engine, which is over here. This is my engine. Then we have clutch, or it is also known as converter of the torque. Then we have transmission over here. Okay. And then this will be my final drive. Okay. And then there will be differential. This is my drive shaft. And these are the driven wheel. Okay. So this depicts the illustration of an automobile powertrain, right? Now this is consisting of a power plant, which is engine in our case, or and if it is an electric motor, electric vehicle, then it will be an electric motor. Okay. Then we have a clutch in manual transmission or a torque converter in automatic transmission. Okay. We do have two types of automobiles available. One is with gear, another one is with automatic gear. So in automatic gear, it will be a torque transmission, while manually it will be a clutch. Okay. Then we have this transmission, which is nothing but a gearbox. Then we do have the final drive, differential, drive shaft, and the driven wheels. Okay. So the torque and rotating speed of the power plant output shaft are transmitted to the drive wheels through the clutch or a torque converter, gearbox, final drive, differential, and the drive shaft. Okay. So the clutch is used in manual transmissions to couple the gearbox to or decouple it from the power plant, right? And the torque converter in an automatic transmission is nothing but one hydrodynamic device functioning as the clutch in manual transmission with a continuously variable gear ratio, right? So the gearbox will supply a few gear ratios from its input shaft to its output shaft for the power plant torque speed profile to match the requirement of the load, right? And the final drive is usually nothing but a pair of gears that will supply a further speed reduction and distribute the torque to each wheel through this differential. Okay. So the torque on the driven wheels transmitted from the power plant is given by the torque on the driven wheel transmitted from the power plant. Power plant is engine or electric motor in our case. Okay. It is given by TW is equal to IG I0 NTTP. Okay. So this IG means it is the gear ratio of the transmission. IG is gear ratio of the transmission. Okay. And this is given by N in divided by N out. Okay. So N is nothing but input rotating speed and N out is output rotating speed. Okay. Then I0. Okay. So this I0 is nothing but the gear ratio of the final drive. It is gear ratio of the final drive, right? Then NT. Okay, if I talk about this NT is the efficiency of the drive line. Efficiency of the drive line from power plant to the driven wheels. And last, this TP is the torque output, is the torque output from the power plant. Okay, so these are the different terms which are used in the torque of the driven wheel, right? So this is our case. Now the tractive effort on the driven wheel. If I talk about some system, okay, say I do have one wheel over here. Okay. Then this wheel, let me draw another wheel. And finally, there will be one more. Okay. So this is our center of the vehicle. Okay. Now what is happening? Here we are available with the road. Okay, this is my road and vehicle is running on the road. So we will produce some tractive force over here at this edge. Okay, this is my tractive effort Ft. Okay, and vehicle is rotating, wheel is rotating in this particular direction. Okay, so this will be Tw, this will be Nw, and say this is my radius Rd, and this is velocity v. Okay, so this is representing a road. Okay, so this is nothing but it shows the tractive effort and the torque on a driven wheel, right? So the tractive effort on the drive wheels, as you can see in this particular figure, now can be expressed as Ft equal to Tw by Rd. Okay, we know this is one physics, right? So now I have this equation Ft, okay, and submit this equation. Let us call this equation as equation number 2 and this equation as equation number 1. This is my equation number 1. Okay, so put or submit 2 into 1. It will give us Ft equal to Tp Ig I0 eta T by Rd. Okay, let us call it equation number 3, right? So the friction in the gear teeth and the friction in the bearings create some losses in mechanical gear transmission, right? So the efficiency, if I talk about the mechanical efficiency, then mechanical efficiency will somewhat reduce. Say for example, if we consider the clutch, then the mechanical efficiency of that component is 99%. If we talk about the gears, then it is ranging from 95 to 97%. If we talk about some bearings and joint, the efficiency would be 98 and 99%, right? So the total mechanical efficiency of the transmission between the engine output shaft and drive wheels or sprocket is the product of the efficiencies of all the components in the driveline, right? As a part of first approximation, the average values of overall mechanical frequency efficiency of a manual gear shift transmission may be, for direct gear it is 90% efficiency, and for automatic gear or other gear it is 85% efficiency. Okay, so transmission with very high reduction ratio will be around 75 to 80%. Okay, and the rotating speed of the wheel driven can be expressed as, can be given by Nw is equal to Np upon Ig I0, where Np is the output rotating speed, right? And the translational speed of the wheel center can be expressed as V equal to pi NWRD by 30 meter per second. Okay. So if we use this equation 4 into equation 5, then final equation of V will be pi NPRD upon 30 I0 meter per second. Okay. So this is nothing but the powertrain tractive effort and the relationship of this powertrain tractive effort with the vehicle speed. Okay. So this is some dynamic equations of the electric vehicles we have seen in this particular session. Okay. There are more dynamic equations that needs to be known by us. So we will see some more dynamic equations as well as the transmission characteristics or power plant characteristics of the electric vehicle, right? So a lot of characteristics are there, and then we will try to find out the vehicle performance in terms of maximum speed of vehicle, gradability, acceleration performance, etc. Okay, so we shall stop here. In the next lecture, we will continue with the dynamic equations, or you can say vehicle fundamentals of electric vehicle. Okay, so we shall stop here. If you have any questions, then you can ask.